Hi guys, Assalamu alaikum. Today I'm going to talk about the influence line for trusses. I'm just going to do one example because the other examples are just going to be using the same technique. And this will drive the point home anyway. So let's go for this truss right here. I want you to find the influence line for force members BG, BC, and HG. Now here, which is very crucial, he's telling me that the loading is at the bottom chord, which means that the load is going to travel this way. Can we have the loading at the top chord? Sure, we can. But then in this case, if we have it here, it's going to be different when the loading is going from A to E. There's one technique which you could do is actually make a table, put the point load at B, find the members, then move that to C, and find the forces again, move it to D, and do that all over again, and then move that to E, obviously starting off with A. So you would have 0, 6, 12, 18, and 24. But for me, I really don't like this technique. I find it a little bit tedious and time consuming, and sometimes you're not concerned about the influence line for all members of trust, maybe 3 or 4 important ones, or that you think are important ones. So usually what I like to do is actually start off with what I'd actually like to do here is actually start off with finding the influence lines for the reaction at A and E. So using Broussard's law, I'm just going to remove the support at A, make that go up, okay? And in doing so, I'm getting the influence line for the AY. So that's ready. So this again is 1 kilonewton using method of triangle similarities. We're getting 0.75, 1/2, and 1/4. Doing the same thing for the influence line at EY, move the support, make that go up, and then you're going to get this influence line right here. So we found the influence line for the reaction at E. Here I just want to point out that again, here the loading is at the bottom chord from A to E. Now if the loading was at the top chord from H to F, then the only part of the influence line that's concerning me is actually this point right here. Okay, but again, I'll leave that up to you. Consider it as an exercise, solve the same truss, and assume that the loading is going between H and F. But for now, we are going to use from A to E. Okay, so we have 2 cases. Case 1 is when, again, since I'm interested in this part right here, I'm interested in this part, this member, and this member. So I'm going to see what happens as the load is moving from A to B, and then what happens when the load is moving from C to E. So now I'm going to take case 1, which is the loading is going to between A and B. Okay, I'm going to make a section, right? In that section, I'm going to expose the forces, assume all of them are tension. So this is my HG, this is my BG, and this is my forces in BC. So you've seen that what I've done actually is I'm taking this section, right, this section right here, instead of this section because of the presence of the load. So the first thing I will do, again, the load here, this case is going from 0 to 6 only. Okay, so going from 0 to 6. So I'm going to take the summation of Fy equal to 0, right? So in doing so, Ey, this is being positive. Again, this is since this is 6 and this is 6, then this angle right here is going to be 45. I'm going to take this part right there, and that's going to be minus FBG cosine 45. Then the force FBG is going to be square root of EY. Okay, so I know that here. Take the summation of the moment about C ysawi 0. Okay, and I usually take this as my positive direction, right? Then I would have FHG negative times this distance, which is 6, also minus 12 EY equal to 0. Then the force HG is minus 1/2 EY. Now I can just simply make summation of fx equal to 0, then minus fhg minus fbc is going to be 0, then fbc is going to be equal to minus fhg, which means fbc is equal 1/2 ey. Okay, so for that now I found the forces from 0 to x. Going now to the case 2, load is between C and D, so this is where this is going. Using again the same section, but working now with this side. Okay, it's easier, right? Now here I'm going to say that, again, using the same techniques, summation of fy equal to 0, then ay plus fbg sine 45 is equal to 0, which means fbg now is going to be minus square root of 2 square root of 2 ay. Take the summation of moment at b ysawi 0, then fhg times 6 plus 6 ay, and then I'm getting fhg equal to minus ay. Summation of fx equal to 0. I'm getting here this in the positive direction, when actually that shouldn't be minus minus. In fact, depending on what I'm choosing up there, it's supposed to be plus plus, but the overall effect is the same. FBC is minus FHG, which is equal to AY. Okay, so now I'm going, since I have all these equations ready, and I have that from 0 to 6 and from C to E, I'm ready to start drawing. Now remember that from this part here, this portion here, I related everything to the reaction at EY. So if I do that, I'm just reminding you what these relationships are. Then FBG is equal to, we want that to be right, okay, is equal to square root of EY, FHG minus 1/2 EY. So I'm going to take this value, the quarter, multiply that by square root of 2, okay, and then get the value of 0.353 kilonewton right here. Then I'm going to take minus 1/2 the quarter, and that's going to be minus 0.125, and this is going to be 1/2, and this is going to be 0.125. So this is telling me what? This is telling me that while the load is between this portion right here, the force FBG is going to be in tension, FHG is going to be in compression, and FBC is also going to be in tension. Okay, so now I'll go to the second part where I related everything to AY, and again the load now is moving from here to here, and just as a reminder, I've proven to you that FBG is minus square root AY, FHG is minus AY, and FBC is equal to AY. So by doing that, multiply the minus square root of 2 times 0.25, we're getting minus 0.35. This is minus 0.707. This is just simply minus AY, so it's the negative of this, and this is just simply equal to AY. So you can see that there is a complete change in member BG as the load is moving along the truss. It goes from tension to compression. This one is going, actually, I'm sorry, this is supposed to be negative and this is supposed to be negative. The whole member FHG stays in compression and member FBC stays in tension. So what do we do with this gap? Okay, this gap here is actually just connect the dots, and we call this actually the panel of change. Okay, where it changes. Here it changes from tension to compression. Here it changed the slope. The slope here is different than the slope here, and the slope here is also different than the slope here. Again, that's what we're calling the panel of change, where I have no direct loading. So as you can see, if you do that, you can have faster ways of finding the influence lines. If you want to go back and find the influence lines from other members, either find them in terms of the reaction AY or EY, or actually now you can find them in terms of the forces that you already found, meaning in terms of FBG, FHG, and FBC. Go maybe to joint B, for instance, and then find everything in terms of FBC if you can. If not, then you can find it on some other things. And actually that will end the influence line for trusses. You guys stay safe and have a nice day.